Welcome back. In our last video lecture, we had a look at how to test hypotheses related to individual partial regression coefficients. And in that case, we had seen how we could use the t distribution or the t-test to test the significance of individual partial regression coefficients. Since we're talking about multivariable regression models, there is another way in another type of hypothesis that can be tested, which is we could test for the overall significance of the multivariate regression model that has been estimated. We will continue to use the same example that we did earlier. The generalized form of the model that was run was yi is equal to beta 1 hat plus beta 2 hat x2i plus beta 3 hat x3i plus ui hat, where the dependent variable yi is child mortality and the independent variables x2 and x3 were per capita GNP and female literacy rate. So the effect of these two variables has been studied on the variable child mortality. The sample on which this output is based consisted of 64 units. We have already had a look at how to interpret this output table. Now, to compare the earlier case and this overall testing of overall significance, I can show you what the null hypothesis, how the null hypothesis differs. In the earlier case, when we were testing the significance of individual partial regression coefficients, our null hypothesis looks something like this. H0 is beta 2 is equal to 0. Or we could test H0 that beta 3 is equal to 0. But remember, and you use the t-test for this type of hypothesis testing. But remember, when you test the hypothesis regarding beta 2 and when you test the hypothesis regarding beta 3, we implicitly assume that we are working on different samples. This is because, on the other hand, when I'm testing the overall significance of the model, my H0 will look something like this. Beta 2 is equal to beta 3 is equal to 0. That is, when I'm testing the overall significance of the multiple regression model, I am testing whether all the partial regression coefficients of the associated with the x variables are simultaneously equal to 0. So in this case, we are working with data from the same sample. However, in the earlier case, when we are testing null hypothesis beta 2 equal to 0 and the null hypothesis beta 3 equal to 0, there is an implicit assumption that we are working with different samples. Even when we use the confidence interval approach, we construct a confidence interval and we say that the probability that beta 2 hat okay, one second. Let me write it in it. Remember the confidence interval approach. In the confidence interval approach, if you're testing for the null hypothesis beta 2 equal to 0, we could construct an interval beta 2 hat plus or minus T alpha by 2 times standard error of beta 2 hat as the confidence interval 95% or 1 minus alpha percent confidence interval of containing the true value of beta 2. Similarly, when we are testing null hypothesis beta 3 equal to 0, we can construct a confidence interval 1 minus alpha percent confidence interval which contains the true value of beta 3. Now if we use the same data, same sample and same data to test both these null hypotheses, these two intervals that we have calculated need not or may not be independent. And this would have an implication on whether or not both beta 2 and beta 3 are simultaneously in these calculated intervals, the probability with which they are in these calculated intervals. So, to sum up, when I'm testing the significance of individual partial regression coefficients, I use the t-test, and for each individual partial regression coefficient, I assume that I'm using a different sample for testing of each partial regression coefficient. This is because otherwise the two intervals calculated for the two different partial regression coefficients may not simultaneously contain both beta 2 and beta 3. So, in order to test a joint hypothesis such as this, we cannot opt for the t-test. Instead, we opt for the f-test. Now, if you remember, the f-test was based on the ANOVA table or the ANOVA technique, which we have discussed briefly in the two-variable case. Now I'm just going to generalize it for the multivariable case. So whether two-variable or multivariable, the relation total sum of squares is equal to explained sum of squares plus residual sum of squares remains true. So in this case, the total sum of squares can be denoted by summation small yi square. The explained sum of squares can be written as beta 2 hat times summation yi x2i plus beta 3 hat times summation yi x3i, and the residual sum of squares remains the same, summation of ui hat square. We had briefly derived this equation in the earlier lecture, so I'm just going to continue from here. Now, based on this ANOVA, we can draw the ANOVA table. So the ANOVA table will look like this. The ANOVA table talks about the source of variation, the sum of squares associated with the source of variation, the degrees of freedom associated with the sum of squares, and the mean sum of squares. So due to regression is the explained sum of squares. That is, due to regression means due to that part of variations in observed yi which are being explained by variations in the x variables. Like I said earlier, the formula will be beta 2 hat summation yi x 2I plus beta 3 hat summation yi x 3I. Just a second. All right. Now, the variation that is being explained by the residual, the RSS summation ui hat square, and the total, that is the total sum of squares, is summation yi square. Now, to find the degrees of freedom associated with each sum of squares, remember yi small yi is capital Yi minus y bar. So when you're estimating the mean y, you lose 1 degree of freedom. So n minus 1 is the degree of freedom, where n is the total number of observations. Similarly, in the residual sum of squares, when you calculate the residual, it will be observed yi minus estimated yi hat. So that will be yi minus beta 1 hat minus beta 2 hat x2I minus beta 3 hat x3I. So since you are estimating 3 partial regression coefficients, you will lose 3 degrees of freedom. So you get n minus 3 being associated with degrees of freedom being associated with residual sum of squares. Now, if I subtract n minus 3 from n minus 1, I'm left with 2, which would be the degrees of freedom of the explained sum of squares. Okay, so the mean sum of squares is nothing but summation ui hat square divided by the degrees of freedom, and over here the same ESS. I don't have the space, so I'm just writing ESS divided by 2. So this is what the general ANOVA table looks like. I'll just point one more thing. If it is a generalized k variable regression model, then your degrees of freedom for TSS remains n minus 1. Here, the residual sum of squares, the degrees of freedom will be n minus k, which means the degrees of freedom associated with the explained sum of squares is k minus 1. Right? And if you are finding mean sum of squares, it will be the sum of squares divided by the degrees of freedom. So, given this ANOVA table, my F statistic can be calculated as the explained sum of squares divided by degrees of freedom, and the residual sum of squares divided by its corresponding degrees of freedom. That is okay. That is if I go back to my earlier slide, this variable from my ANOVA table, it is this divided by this, that is f. Or the f statistic. Now, testing the significance of the f statistic, will be equivalent to testing. Now this would follow. So, testing the significance of this f statistic, where it falls, whether it exceeds the critical value of f, can help reject our null hypothesis. And if the f statistic so calculated is less than the critical f value, then we can reject the null hypothesis. I'm sorry, I missed that. Wait, if the calculated f statistic is greater than the critical value of read from the f table, you will reject the null hypothesis, which would mean that the variables selected in this model are simultaneously significant. On the other hand, if the f statistic that you have calculated is less than or falls in the acceptance region, then you may not reject the null hypothesis. You may make the same decision of accepting or rejecting the null hypothesis based on the p-value of the f statistic. Remember, p-value gives you the lowest level of significance at which the null hypothesis can be rejected. So, if your chosen alpha is, say, 5% and your p-value is less than 5%, then you can always reject the null hypothesis at 5% level of significance or confidence, 5% level of confidence, and so on. In the example that we saw, the ANOVA table would look something like this. So you have the source of variation, which is the explained sum of squares, the residual sum of squares, and the total sum of squares. The explained sum of squares came up to 257,362.4, whereas the residual sum of squares was 106,315.6. Total sum of squares is 363,678. So this was the sum of squares. The degrees of freedom associated with explained sum of squares is equal to k minus 1. So that's 3 minus 1. N minus k, which is 64, minus 3, which is 61, and n minus 1. Right? So using calculator, you can calculate the mean sum of squares. It comes up to, sorry, 681.2, and 106,315.6 divided by 61 is 1742.88. So the F value would be divided by, which is around 73.8. Now remember, it follows an F distribution. This value is supposed to follow an F distribution with, say, 5%, so that's 0.05, and degrees of freedom 2,61. Now to find the critical F value, you're supposed to use the F distribution tables, which is given at the back of the Clark's tables or your Gujarati book. So from there you can see that the critical value is 3.15 for degrees of freedom 60, right? 61 actual degrees of freedom in the denominator is 61. Since that is not given in the table, we take the closest value, which is 60. So the 5% at 5% level of significance, the critical value is 3.15. Since 73.8 far exceeds 3.15, we can safely say that this F statistic falls in the critical region, and therefore we may reject the null hypothesis that beta 2 is equal to beta 3 is equal to 0. Remember, this same test can be generalized to the k variable case. Even when you have k variables, your null hypothesis will be beta 2 equals to beta 3 equals to up till beta k is equal to 0, and your F statistic will be calculated based on the same ANOVA table constructed for the model. Now once again, from the exam point of view, I need you to know how to calculate the F statistic if, say, the sum of squares is given to you and the model that has been run, the regression model whose output is given, is known to you. We are not interested in too much of derivations at this stage, but you need to remember, if you are given the sum of squares, you need to remember what is the degrees of freedom, and how, if you have both sum of squares and the degrees of freedom information given to you, how to calculate the F statistic and test for the overall significance of the model.